So welcome to, this is Friday of week 6, which is a kind of major day because we're at the halfway point. Because it's a 12-week quarter and we'll be at week 6. We're almost done with it. So hopefully it's going well. You've been working hard and you're getting ready for next week's exam because week 7 on Friday is the exam 2. So let's go ahead and I'm going to share my screen and let's take a look at that quiz. Okay, so here's the quiz. And it's a 2-meter tall person walks away on level ground from a 5-meter lamppost at a constant rate of 0.8 meters per second. How fast is the shadow of the top of the person's head moving when the person is 6 meters away from the lamppost? All right, so I kind of gave you a step-by-step process last time, and I just did step 1, which is read the question. Remember what step 2 is?
Draw a picture.
Draw a picture. And I'll tell you know, drawing a picture is probably not something you're going to be able to do embedded into the test so easily. And that's fine on this because, you know, you can use a paper and you could use paper under your computer if you want for the quiz. But I prepared ahead of time and I drew a picture. So here's a picture. We have a lamppost that's 5 meters high. We have the man that is, or the person actually, is 2 meters high. And then we need to label some variables. I'm going to call X the distance from the lamppost to the person. I'm going to call H the distance from the lamppost to the shadow, the head's shadow. And then it helps to note that this other piece over here is H minus X. Any questions on the picture? Nothing tricky here, but you got to have that picture down. Any questions? Okay, and again, I don't expect you to draw a picture embedded into the quiz. That's hard. There are ways of doing it, but it's really hard. So let's not. Instead, draw it on paper so you can refer to it. So that's the first step. And I want to let you know that I gave you the warning about this particular section. This is pretty tough. So, you know, some of you might have gotten this one. If you know how to do it, this is actually a really easy problem. It's the knowing how to do it. Does that sound right? My guess is it was all or nothing. Either it was really easy or you couldn't get it figured out. Sound about right? I don't see y'all jumping in. Okay, yeah. So we'll see which side you're on when I grade it, but you'll see it's not too bad. But then you have to know what to do. So now we're gonna write down what we know. We have the word rate, and that's important. In calculus, what is the word rate? What does it associate with?
The derivative.
The derivative. And notice that it is the rate at which the person moves away from the lamppost. So it's the change. It's the change in X with respect to time. Okay. So what I'm going to do now is I can say dx over dt is equal to 0.8. Any questions so far? Okay, we want to know how fast the shadow of the top of the person's head is moving. All right, so that is going to be the change in h over the change in time. So I like to type in dh over dt equals question mark, because that's the question. If you don't know what the question is, it's very hard to find the answer. Any questions so far? All right, so now the next step is we need a relationship that relates h and x, because that's the 4 steps, I guess, in this list of steps to do. So how do we find a relationship between h and x? And the hint is you got to go back to your geometry time. And for some of you, it might have been, a year of high school. They might have called it geometry. They might have called it integrated math, but you did it at one point. And remember, okay, the key on this one is similar triangles. And yeah, so 5 is to h, 5 is to h as 2 is to h minus x. Does that make sense? Because 5 is the long height and h is the long bottom. 2 is the short height and h minus x is the short bottom of this short triangle or small triangle. Okay, so what we can do again is 5 is to h as 2 is to h minus x. And let's type that in. Any questions so far? Okay, we could jump to the derivative now, but it's a lot easier to do a little cross multiplying first and just say 5 times h minus x equals 2h. So I'm going to put that in here. Then I have to work with these fractions. So 5 times h minus x equals 2h. So I haven't done any magical geometry or algebra, but if you don't think to do it, you won't get it. Okay, then what's the next step in the process? In the step-by-step process? Distribute the 5, we don't have to, actually. In the step-by-step process. Solve for h, no, we don't have to do that either. I'm gonna do the process. Hint, calculus. I'll jump it in. Just take the derivative of both sides to implicitly differentiate. Not really. It's not any easier to solve for h because the derivative is very easy here. Might as well do an easy derivative now. Jump into it. So I'm just going to one more time. That was weird. Let's try again. There we go. So now I'm just going to take a derivative. And we're going to have 5 times dh dt minus dx dt equals 2 times dh dt. Any questions on that? Okay, we now have the derivative. Once you've taken the derivative, then what do you do? So what's the last step after you've taken the derivative implicitly? Yeah, we plug in. And we know that dx dt is 0.8. Just notice, I told you that the person is 6 meters away. You never need to know that, okay? That's just a red herring. You never needed it. Turns out no matter where he is, the shadow is always moving the same speed. So, but we do know, we do need the dx dt is 0.8. So let's plug in. So the dx dt becomes a 0.8. Any questions on that? Okay, now we find dHdt, and we can multiply the 5 through. I'm going to do it in my head if that's okay. You multiply the 5 through, you subtract the 2 dHdt, add the 0.8, and then divide by 3. Okay, and again, it's just very basic algebra steps. I'll let you do it yourself too. You should be able to do that. So we end up with dHdt is equal to, and it was, let me try and remember again. I think it was 0.8 divided by 3, I believe. And I'll double check because I can't see the question as I'm going. Just a second.
Larry, you're multiplying the 0.8 by 5/3.
Let me see. Yeah, unfortunately, I can't see it because Zoom's not letting me in. Zoom does that sometimes. Let me try this. It's not letting me to the bottom. Oh, I know. Maybe if I do this, that'll work. So let me double check again. So we get 3.8 over 3. No, that was right. So the idea here, oh, that's 5 times 0.8. Yep. There's a missing 5. That's better. Okay, and 5 times 0.8 over 3. 5 times 0.8 is 4. You just get 4/3. That's better. Any questions on that? Any questions? So again, there's no step here that's like hard to follow. Do you agree? But coming up with yourself, especially, I would guess that this step right here, the 5 over h equals 2 over h minus x, that was probably a hard step for most people. Maybe I'm wrong. Maybe it's drawing the picture. But it's not the calculus typically that's hard, right? That was an easy derivative to take. But it's the setting up the picture and the equation from the words. That's usually the tough part. Any questions at all on this particular quiz? Any questions? Okay, so if there's no questions, let's come up to the kind of plan of action for today. Are there any questions about anything else? Any questions? Give you a minute or two, because we have kind of an easy day today. Unlike Wednesday. Wednesday is a tough one. Today's an easy one.
I have a question.
Sure.
So I noticed that in the homework yesterday, we had some problems that had to relate to volume and all that sort of stuff. Will we ever see that on the test?
Yeah, I could have given you, say, volume of a sphere, right? In the example on Wednesday, I gave it a volume of the sphere example. Do you remember?
Well, I'm not talking about that in regards. I'm talking about the volume, but there's also a set height in there, and you have to like find the rate. Like it's kind of hard for me to put it into words, but you know, but pretty much it's the volume of the shape overall, and then you have and you need to find the rate of the volume.
Right. And that's how all related rate questions are, is that you have some equation that comes from the words. And if the words are about volume, then you're going to have a volume formula equation. And that could be a sphere, it could be a rectangular solid, it could be a cylinder. There are lots of things that you've learned about volume. So based on that, you write down the equation and then do the steps. You take the implicitly differentiate, plug in, and solve.
And for the test, will we need to say memorize some of those equations for volume and for shapes?
You should know the very basics. So cylinder,
just the very basic.
Cylinder, sphere, rectangular, solid.
All right. Okay. All right, thank you.
I'm not going to ask you like for the equation of the volume of a dodecahedron.
Okay.
That wouldn't be very nice. But I think that I could feel comfortable about cylinder, sphere, and rectangular solid. So if you need a reminder, sphere we did last time, 4/3 pi r cubed. The cylinder is 2 pi r h. And the rectangular solid is length times width times height.
All right.
Do you remember those three?
Makes sense.
And my guess is, again, you didn't tell me what specific kind of volume you were looking at, but my guess it was one of those, was it?
Yeah, it was something like that.
I mean, it was one of those 3 geometrical shapes.
Not to interrupt, Larry, but it was an upside down pyramid, if I remember correctly.
Okay.
And it was asking for the height.
Yeah. So pyramid, I probably wouldn't have you have memorized. I have it, but but for the homework course, you can look it up. You know what I mean? Just type in Google volume of a pyramid and it'll give you a formula. You know what I mean? Within the first couple links. But in terms of the exam, the 3 I just said are the 3 that you're responsible for. And I haven't written the exam yet, so I don't even know if I'm going to put one on. And if I do, I don't know which one. But I'm probably going to write the exam tomorrow is my plan. Tomorrow or Sunday.
All right.
Especially Sunday, miserable weather. So it might be a good day to like hang out inside and for you guys study and for me write your exam. Okay. Does that help?
Yeah, that did help. Thank you for answering my question.
Yeah. And it is tough because there's so many formulas out there and which ones should you know? So if I tell you those 3, then I feel comfortable if I asked you one of them. Okay. Anything else? Anything else? Okay, so if there's nothing else, I'm going to get into differentials. And as I mentioned in the intro, is that today's kind of a review. There'll be a few words that you haven't seen before, but we've done this stuff before. And I think you'll understand. I think you'll believe me when I start working all this out. So if you have a function, let me just start typing some function. And I'm going to do it in general before I do the example. If you have a function, let's say y equals f of x. Sound like a good function? That's the general function. Then in calculus, of course, what we can say is that dy over dx, okay, and what I'm about to write is a bit silly, but I'm going to write it anyway. Dy over dx equals f prime of x. Do you all agree with that? So Leibniz equals Newton is all that says. Okay, so we know that. So the next thing I want to look at is thinking about dy over dx as a fraction. We do that a lot, even though it's not perfectly precise, but it works in basically anything you ever do. So we can rewrite this. Think about, your early days of fractions. Most people hated fractions, right? Oh, that's supposed to be sorry. That should be a dy over dx. That's an error. Typo. Okay. So if you hate fractions, what do you do to get rid of the fraction? So how do we not have a fraction? Okay, it's not a hard question. If we have dy dx equals f prime of x, and we don't want to have a fraction, what can we do? And then you see all jumping in. It's easy. Yeah, we multiply by, what do we multiply by? Not by 7. Yeah, we multiply by dx. So we could say that dy is equal to f prime of x dx. And I'm going to make that bigger because it's important. And I've mentioned a few times, there's issues with writing that because it's not really a fraction, but this is the way we do things. So we could say dy is equal to f prime of x dx. Well, dy isn't really defined because there's a limit as, h goes to 0 kind of stuff. But if you kind of ignore the limit, then dy is the same thing as delta y. And dx is the same thing as delta x. Okay, that's if you ignore the limit. But if you ignore the limit, you lose a little accuracy. Does that make sense? So let me write it in different notation. And I'm going to write it with delta y. And it's not going to be equal anymore because we're going to lose a little accuracy. It's going to be approximately equal to f prime of x times delta x. So the nice thing about this, mathematically, this is very easy to do. I didn't really do anything hardly. Just change the symbol, realize that it's an approximate instead of an equal sign, and multiply it at the beginning by dx. Okay, that's a big deal. What this tells us is if we want to approximate the change in y, we can take the derivative at the initial value and multiply by the change in x. And as long as delta x is small, it's a pretty good approximation. If delta x is large, it does not work. So let me give you an example in terms of a picture. Let's suppose we have something like f of x equals sine of x. And the idea here is that the tangent line is y equals x. Any questions so far? So if we focus at x equals 0, then the tangent line and the curve are close to each other forever. What do you think? When do they start like veering apart? Because obviously if I put x equals 12, it's not going to be a good approximation at all. So when do you think it starts veering apart around? Around 1, maybe 0.8, just somewhere around here. And then all of a sudden, it's a terrible approximation. But as long as you're close, as long as your delta x is small, then this works. Any questions on that? So again, this should feel like a review, which is okay. We're going to have some, we're going to have examples, and then we'll have technical stuff and applications. So notice that as long as you stay pretty close, y equals x and y equals sine of x are basically the same function. And you may ask, what's the point of all this? Why would you ever, like if you have y equals sine of x, why would you need to approximate it with y equals x when sine of x is easy? What do you think? Any ideas? What the point of this is? I don't see it. It's not always easy functions. Well, this isn't easy either. So it may seem easy, but I'm going to give you a challenge. Okay. No using a calculator. You have to do it in your head. You can do it by hand too, paper and pencil. What is the sine of 0.01? See if you could do that. What is the sine of 0.01? No calculators allowed. Okay, and the answer is, if you had to get the exact value of the sine of 0.01 without using a calculator, it's fruitless. You'll never get there. Do you agree? But if we know that for small x, that the sine of x and x are the same thing, I can say that the sine of 0.01 is about 0.01. Because f of x equals x, I could do that in less than a half a second. All I do is repeat the number. Do you see that? And this specific example is so important that in physics, there's a word for it. There's a sentence for it. Anyone in physics or had physics? Any of you guys have had physics or in physics? I don't see y'all jumping in. Okay, so you had it, Bruno. Okay, so next quarter is not going to help. Did you hear that in your physics class? The word to use x instead of sine of x. Okay, if you haven't, it's called the small angle approximation of the sine of x. There's actually a whole word for it. Everyone talks about it because that's what everyone does in physics. They say, hey, as long as you're small, as long as you're not very far from 0, the sine of x is x, and that's good enough for anything you care about. Any questions on that? You vaguely remember. So you've seen it before. So I'm not just, saying some myth. It actually does happen. Okay, I don't teach physics, but I watch a lot of physics lectures. And I see that all the time as a small angle approximation of sine of x. It's so much easier to use x than it is to use sine of x in so many different applications. So this is a very, very important process in trying to use something easier to approximate something hard. Any questions on this idea? Okay, let me go back. And let's do a few more things. So again, we could say delta y equals f prime of x delta x. I can rewrite that in a different way. There's lots of ways of writing these things. So we can also say delta y is f of x minus f of your central value. So that's like f of x minus f of a. And what we're doing is we're going to plug in a. So we can say now that, let me grab it. F of x is approximately is approximately equal to f of a, because remember we have f of x minus f of a, you can add the f of a to both sides, and then we have plus f prime of a times delta x. Any questions at all on this idea? And I'll let you know that sometimes books, including our book, they get lazy and they don't even bother with the delta x. And I'll let you do that too. So what you can do is you can rewrite this. And instead of delta x, just say dx. Even though technically it's not perfect, but the book uses it. And why is it that it's easier to do dx than delta x? It's not a math thing. Yeah, writing it. So especially on a test. So on a test, you can write down dx instead of delta x, and that's fine. Technically, dx is infinitesimally small, and delta x is not. Delta x is small, but not infinitesimally. But in this section, you can get away with it. Any questions on this idea? Okay, I actually copy and pasted a picture that the book had, so I didn't have to do it. Because it was quite complex and it was a lot easier to use theirs. And it does all the stuff that we're doing. So I want to look at this picture again. It's a pretty complex picture, so don't get too overwhelmed. And that is, we have our function. The function is in blue over here, y equals f of x. And then the tangent line is what the book calls y equals L of x. I kind of like T better, but the book uses L. L for line, I think. Okay, and the idea here is A is kind of your central focus. That's your starting value, your starting point, and going to move off from that point. Well, you can see if you're looking at the curve, you're up here on the blue curve. If you're looking at the tangent line, you're a little bit lower. Any questions on that? So the distance from our point, our horizontal distance from the initial point to the final point is dx. Okay, and again, often called delta x. I'll let you choose which one to use. Dx is easier to type. Any questions on that so far? The distance from the x-axis at a plus dx up to the curve, that's f of x. Okay, the distance from the x-axis up to the line, that's L of x. Okay. So then you could do some more. Instead of the function, we want to look at from a comma f of a. And then dy will be how high you have to go from a comma f of a to the line, whereas delta y is how far you have to go from f of a to the curve. Any questions on that idea? And the idea is that if we have a function and we have a very small delta x or dx, then the error, the vertical distance between these 2 points here on the tangent line and on the curve will be small. And that's what you want. Any questions on this picture? It's pretty complicated. Any questions? So I'm going to hold it for a minute because I want to make sure you get this picture. It's an important picture. It's kind of really the essence of calculus. It's what calculus is all about. It says that we have a curve, and you can, instead of using the curve, you can use a tangent line. And the tangent line and the curve are very close to each other, as long as you zoomed in enough. And we've had that from day one. So now this is just the same thing, but all the notation written out. Any questions at all on this picture? Okay, again, it's worth playing around with. All right, so let's do the example that we were looking at. We're on the Desmos. So let's suppose that f of x equals sine of x. Okay. And let's suppose that a equals 0. And how about dx equals 0.01? Okay, and then from Desmos, we saw that was we'd get a good approximation if you're that close to the origin. Are y'all good with that? And now let's compute these different pieces in the picture. All right, so the first thing, and you better be able to all tell me this without even hardly thinking, what's f prime of x? This is a biggie, by the way. F of x is sine of x. What's f prime of x? Yeah, that's cosine of x. Okay, you got to have that one down in your head for basically the rest of your life if you're going to be an engineer, and definitely the rest of the year if you're going to take the first year of calculus, because that one, the derivative of the sine is the cosine. Okay, and I want to remind you, it's always radians. Any questions so far? Okay, and then we can do some more. A lot of these are easy. What's f of 0? That's supposed to be easy. It's not a trick question. Yeah, f of 0 is 0. And what is f prime of 0? Should also be pretty easy. Yeah, that's 1. Cosine of 0 is 1. Any questions so far? Okay, so now we can start, once we have all that information, now we can start plugging everything in. So now we can say that f, what we wanted to look at, is f of 0.01. Any questions on that? Okay, now without a calculator, we can't get it exactly. Okay, even with a calculator, you can't get it exactly, it turns out. But what we can do is we get it approximately. So f of 0.01 is going to be approximately f of 0 plus 1 times f times 0.01, because delta x is 0.01, or dx. And that, of course, is 0.01. And kind of the whole point of this is we can do this immediately. I mean, there's like no calculation to do hardly at all. Adding 0 to something is pretty easy. Multiplying by 1 is pretty darn easy. Okay. And it turns out, because f of 0 is 0, we can say that our dy will be also 0.01. On the other hand, delta y, that is going to be f of 0 minus 0. And f of 0, I can't do that in my head, and my guess is you can't either, unless you have a really weird sense. but I can do it with Google. Sine of 0.01 and it's 0.0099983333. Is that a good approximation or not? Was using the derivative approximation or the tangent line approximation a good approximation? What do you think? Yeah, we're actually correct to 6 decimal places of accuracy. Do you see that? So for 6 decimal places, it's correct. So this is a very good approximation. And that's why everybody uses it for the sine of x, because it works. Okay. On the other hand, if instead of say 0.01, we tried 1, take a look and see if it works. So now let's think about, let dx equals 1. It's going to change a lot. Okay. Calculus isn't going to change at all. So if dx is 1, we can recompute some of these things. And what we can do is we can say that dy is also 1. Okay, that's the nice thing about the small angle approximation is dy is just your value of x. So dy is 1. And delta y, that we have to figure out. Well, let's go back to a calculator. And you get 0.8414, a bunch of things like that. Let's copy it. So delta y is this mess. All right, is it a good approximation now? If you use 1 instead of 0.01. What do you think? Yeah, now we don't even have 1 decimal place of accuracy. Whereas if we're at 0.01, we had 6 decimal places of accuracy. So you do have to stay really close. If you don't stay really close, things go bad. Any questions on that? Okay, so now let's do an example. Suppose you want to measure the volume of a sphere. Okay. And you can measure it. So you're going to what you're going to do is you're going to use a ruler. All right, I'm going to ask you, I'm going to let you decide. How accurate is a ruler? If you're going to use a ruler, how much is your error if you're going to measure the radius of the sphere? Okay, so you got a ball basically, and you're going to use a ruler to measure the radius of that ball, which you can do. Okay, I'm looking for a number here. What's your? I'm going to let you decide. This isn't a math question. This is a practical question. Okay, whatever you have at home, whoever is first to jump in and say how good you can measure the radius of the sphere, we're gonna go with. How good can you measure it? Okay, and if you say I can only measure it but within a foot, I'm gonna say you need a new ruler. So how accurate do you think you can measure it? If I asked you to, find the nearest ball that you have at home, you probably have a ball, whether it's a baseball or a soccer ball or something, or a softball. And I said, go out and get your measuring stick, your ruler, and measure it. And you came back, how accurate do you think you can get with that measurement for the radius? Somebody's got to chime in. Okay, all right, so we'll do inches is okay. I tried to do metric system, but we'll go with inches. So 1/16 of an inch. You can measure the radius within 1/16 of an inch. Not within. Any questions on that? Okay, and that might be true. Rulers have 1/16, and as long as your eyes are good enough, you should be able to do that. So here's the question. If the radius, let's go, if your measurement is, so you're going to measure a ball. I'm going to ask you another question. Here's something I don't know. This is, if you take Bruce, you'll get this a lot better than me. What do you think the radius of a baseball is, since it is World Series time? What's your best guess? I'll take anything because I don't know. I've seen a baseball. Okay, if the measurement is 2 inches, what is your error and your approximate error in finding the volume? Any questions on the question? All right, so first thing, let's see if you guys can tell me. What's your best guess at the volume, given that you just measured it 2 inches for the radius? So how do you get the volume? Let's not worry about the error yet. We're just getting the volume. Pi r squared, close, except it's not a circle, it's a sphere. And you got to remember, I did this a couple days ago. What was the equation of the sphere? The formula for volume? I don't see y'all remember. It's 4/3 times pi times r cubed, which is equal to, well, if r is 2, that's 8 times 4/3, which is 32/3. Any questions on that? And then if we want, a few decimal places or whatever, we can just type it in. So 32/3 times pi. And you get this beautiful number. Any questions so far? Okay, that's one way of finding the volume. What's another way of approximating the volume? Okay. And actually, that's the volume. That's not what I want to say. How about the error? Error in the volume. And how do we get that? And remember, you're able to measure it to 1/16 of an inch. That was what you decided. And by the way, 1/16, in case you don't know, is 0.0625. That way you don't have to write fractions. Okay, so the idea is we know that we're off by 1/16 of an inch at most in either direction. So what we can do is we can take our 2 and we can look at, say, what is V of 2.0625? Any questions on that? Well, what we can do is we can just put it into the formula. So that's going to be equal to 4/3 pi times 2.0625 cubed. Any questions on that? Okay, now it's good. We don't have the error yet, but we'll get there. So let's put that into the calculator. So 4 divided by 3 times pi times 2.0625 cubed. And what we get is 36.751111, etc. Okay, so now what we can do is we can say, well, what is the error? And I'm going to do the high side of the error. You can do the low side the same way, but I don't want to waste your time. So the error now, and this is a true error, is going to be this 36.75 bunch of ones minus the 33. And you get 3.2407, etc. Any questions? Any questions on this calculation? Okay, and this is delta y. And by the way, you can also go and subtract instead of add. Okay. So in other words, you can look at, instead of 2.0625, you can go 2 minus 1/16, and then plug in and you'll get something else. Okay, and that'll be the error on the left-hand side instead of the right-hand side. So we just did, let me write down right error. This is the right-hand side error. Any questions on that? Okay, well, that's a non-calculus way of doing it. How do we do it using calculus? Yeah, we take the derivative. So what we can do now is we can find v prime of r. And v prime of r is the derivative of 4/3 pi r cubed, which is just 4 pi r squared, which is kind of nice. Okay, now we're plugging in 2. So v prime of 2 is equal to 16 pi. So let me stop for a second. Any questions on what I just did? Okay, so once we have that, then we can come up with the error. And the approximate error will be the dy, will be the dy. Okay, so the dy now is going to be the derivative, which is 16 pi, right? So it's f prime times dx times 1/16. Because that's how much we're off by. And look how beautiful that is. I hope you don't need your calculator to tell me what this is to a few decimal places. In normal years, we have a contest on Pi Day, but this year, I don't think we're allowed. Yeah, it's 3.14159265, et cetera, et cetera. Good enough. Okay. So what do you think? Do you think it's a pretty good approximation? Do you think it's a disaster to use calculus instead of not using calculus? Okay, and if you notice, using calculus, I didn't need a calculator. I had no pi was, but you know, to a couple decimal places, which maybe one decimal place is all I really care about, then I've got my error down. So my error is no more than 3.1, 3.2. So around that, we're off by 0.1 inches in terms of the error, which is not that big a difference, considering that our error is going to be around 3. So we're only off by about 3% or so. Anyone lost on what I just did? Any questions on this? So far, so good? Okay, so now what I want to look at is, first thing, a couple definitions. And it's actually propagated error. So propagated error, that's the error that happens when you take a measurement. Okay, so, and then mathematically, propagated error will be defined by the difference between your estimated value and the true value. And actually, it's typically in absolute value. And that's called the propagated error. So again, you've calculated the error. You've calculated the function with your ruler. You only did it with the radius. You used that equation, 4/3 pi r cubed, and that changed the error, right? We originally had only 1/16 for your error in radius, but your volume error is 3, okay? So the propagated error got big because of having to deal with the formula. Any questions on that idea? So that's a propagated error. The next error, and again, this is almost not even math. This is more science. It's used everywhere in science. The next is a relative error. Okay, let me ask you something. if I measured something and I was off by a meter, do I have a good measurement or do I have a bad measurement? Do you think, am I pretty close or am I not pretty close? Am I off by a meter? I'm off by a full meter. Yeah, it depends on what you're measuring. So if I were measuring the radius of a baseball and I was off by a meter, what do you think? Yeah, really, it's not just bad. It is horrible. Okay, being off by a meter in measuring a baseball is just stupid. I hope you know that. On the other hand, what if I measured the radius of the sun and is off by a meter? What do you think? Yeah, that's better than okay. If I could really do that and I could verify that I was really only off by at most a meter, I'd probably win a Nobel Prize. Good luck measuring the sun off by 1 meter. That's not going to happen. Okay. So it's not the error that's the most important. It's what's called the relative error. So it's not whether you're off by a meter or not. It's how much you're off by compared to how much the original thing was. So the relative error is defined. I'll just write RE for relative error. Does it let me do it? This one. Yeah, triple equals defined by. And what we're going to do is we're going to take the propagated error and we're going to divide that by the value, by the measurement. Okay, another way of writing that is we can say that the relative error is going to be delta, is going to be, let's fraction. The propagated error, that's going to be our delta y. Over y, because the measurement is y. Okay, and for most purposes, that's a lot more important. Because if you're in chemistry and you're measuring, you know, if I said I was off by, you know, 1/100th of a centimeter, that sounds great, doesn't it? Right? If my error was only 1/100th of a centimeter, that sounds really good, doesn't it? Okay. Yeah, it doesn't sound good if you're measuring the distance from the electron to the nucleus of a hydrogen atom. 100th of a centimeter is absurdly bad estimate. Okay, if that's what you're off by. So what you want to do is you want to take that ratio. You want to make sure that you're taking into account how big the thing is and not just how much your error is. And that's what the relative error is. Any questions on that? Okay, and then finally, there's a percentage error. The percentage error is very easy once you understand relative error. I'll just call it PE. Okay. Oh, sorry. I'll just call that. That doesn't. I'm going to go percent E. I think it's better. And that's going to be the propagated error. Divide them by the measurement. And this is easy. Times 100. Sometimes you'll put a percent there. So it's times 100. And a lot of people do that because that's what you care about is what's your percent error? Are you off by 1%? Are you off by 20%? There's a huge difference. Any questions on the idea? Any questions? Okay, so let's look at this. So suppose you want to find the area of and I saw a equilateral and equilateral triangle. It's equilateral. Is that right? Okay, so you want to find the area of an equilateral triangle. You measure one of the sides. Let's just write MEA. As 3 centimeters with an error of 0.2 centimeters. And the question is, find everything. Find the propagated error, relative error, percentage error. Using calculus. All right, using differentials. Any questions at all on the question? Any questions? All right, so what do I have to do? What do I have to do that you may not be able to do? And it's not hard calculus. Calculus is not the hard part of this one. The thing that you probably don't know or don't remember. Don't have the true value. That's okay if you don't have the true value. We're going to be using our calculus, so it's okay. We'll get an approximate value. Okay, let me ask you. Maybe you all know, and maybe I was wrong. How many of you remember the area formula for an equilateral triangle, given a side? Since none of you said that you didn't know, I'm going to assume you all know that one. Am I right? So maybe put in the chat box because you all remember what it is. Was it right that that's the hard part? Okay, I don't see everyone jumping in. Okay, well, if you don't remember, let's Google search it just for fun. So area of equilateral triangle. I'm going to type the whole thing, it just knows. Okay, and it's square root of 3 over 4, a squared. Okay. All right, so what we can say is capital A, the area, is equal to the square root of 3 over 4 times a squared. And we also know that the dA, d capital A, is equal to the square root of 3 over 4 times 2a, or we can say it's the square root of 3 over 2 times a. Any questions on the calculus? Do you agree the calculus is actually the easiest part of this whole problem? That was not a hard derivative? The hardest part is probably remembering the formula. Okay, so now that we know that that is the dA, now we can start plugging in. we know that our error is 0.2. So I can plug that in. So let's do this. So square root of 3 over 2 times 0.2, which is, by the way, the square root of 3 times 0.1. Okay, and you may or may not remember the square root of 3, but we can always do SQRT of 3 if you don't remember it. And it's 1.732 is probably good enough. Any questions on finding DA? Okay, so that was DA. Okay, and that is our approximate propagated error. Let me write that down. All right, so we got the first one. How do we get the relative error? Over 0.2. Okay, so the denominator on the relative error, it's over here, is y. It's not a dx, it's a y. So we got to figure out y is, well, to find y, we plug in 3 into the area equation. Any questions on that? So notice that a of 3 is equal to the square root of 3 over 4 times 9. Or 3 squared, might be easier to type that way. And that, square root of 3 over 4 times 9, let's do that. Is 3.897. Let's just do it this way. Grab a bunch of decimals. Any questions on how I got that? Nothing magical. Okay, now we're ready to get the relative error. So the relative error will be, by the formula, the propagated error over the measurement. Well, our measurement was a 3.89711. So let's write this down. So we're going to take our DA, which is 1.732, and divide by 3.89711. And you probably want a calculator for that. So 1.732 divided by that guy. And you get 0.4444. Interesting. I'll go 3/4. Any questions on that? Wrong one, that one. Is that clear? Okay, now comes the easy, let me write down, that was our relative error. Okay, what's our percent error? This is easy. You shouldn't need a calculator. So what's the percent error? If I know the relative error is 0.444. Yeah, 44.4% is equal to the percent error, percentage error. Okay, by the way, that's a pretty big error, isn't it? Okay, so that's just a note. You know, it's very important to know, do you have a big error or a little error when you're doing this kind of stuff? Okay, it's kind of a percent change. Any questions on this idea, on this process?
Larry, I'm still lost on how you got 1.732. Like it's A2
Up here?
Yeah, in the
A was 3.
It was 3.
You measure one of the sides as 3 centimeters.
Okay.
So all I do is plug in. So I plugged in the 3 right there.
Okay.
Yeah, nothing fancy, I promise on that one. So A is just whatever your measurement is, that's what your A is. Does that make sense?
Yeah, thank you.
Okay. That's all I need to say. Do you agree that today was a lot easier than Wednesday? Just applying a few formulas and that's it? Yeah, most people find Wednesday was the hardest day of the entire quarter. Okay. Some people don't like epsilon delta. But most people think related rates is a tough one. There's one other that's coming up in a week or two that people have trouble with. More word problems. All right, well, I think I'm going to stop the share.